Bum 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 ba-da-dum. A duck walked up to a lemonade stand, and he said to the man, run in the stand, hey, bum bum bum, got any polynomials? And the man said, hey, I thought you were going to ask me for grapes, but yes, of course I've got some polynomials for you, because this isn't a lemonade stand at all. This is in fact our 7th class of Unit 7, Factoring Quadratics Part 2. Now remember, factoring is all about mental math and trial and error. Factoring, especially when it comes to quadratics, is a lot like solving a puzzle. Finding the pieces that fit together often takes a bit of time and rarely happens on the first pass. But the more of it we do, the more mistakes we make, the more practice we get, the easier it becomes. So let's do a little practice and make some mistakes. We've got 3 polynomials in front of us. Using the tools that we've learned thus far, I want you to take each one and factor it into the products of some polynomials. Take a minute, pause the video, see how far you get. Let's go! Now for number 1 and number 2. Both of these we can describe, as we did last class, as quadratic trinomials. Their degree is 2, and they have 3 terms. And as we saw last time, quadratic trinomials are often the product of 2 linear binomials. So that immediately tells me something about the structure of their factors. We also saw that when our quadratic trinomials have at the front that invisible leading coefficient of 1, there's a funky little pattern that we can follow. Well, we know at the front of our factors, when we met wet back out, we need to get back to our quadratic terms. So in the front, in our first answer, we need something that multiplies to get h squared. In the front, in our second, we need to get something that multiplies to j squared. And at the back, I know that these things here taking up the rear, they need to do 2 things when the leading coefficient is 1. So I know that not only when I met wet should they multiply to get me back to the number at the back of my polynomial, so either 16 in my first case or negative 56 in my second. I also know that these numbers need to add to get the coefficient of our linear term. So in the first term, or in the first problem, right, they need to add to negative 8, and in the second, they need to add to that invisible negative 1. So at the front, if I need an h squared in the first one, well, the only way I can get h squared is from h times h. And for the back, well, let me think about some possible cases for 16. Here's an opportunity for us to be strategic. 16 could be either a positive number times a positive number, or a negative number times a negative number. Seeing this minus sign in the middle, which of those should immediately tell you it is? 5 seconds, go! 5, 4, 3, 2, 1. Well, if I need a negative middle term, it must come from 2 negative numbers. So it can't be a positive times a positive because there's no way I can add positive numbers to get a negative 8. So, thinking of options, 16, knowing it needs to be a negative number times a negative number. It could be negative 1 times negative 16. It could be negative 2 times negative 8, or negative 4 times negative 4. That last one should do the trick. So I'm going to slot in my h minus 4 and h minus 4 as my factors. Well, what if I don't believe that? Well, I can always check my work by doing a little met wet. So I believe that the h times h will get me h squared. I believe that the negative 4 times negative 4 will get me the 16. I chose those strategically. So when I check, all I need to do, thinking strategically, is check my middle term. Well, h times negative 4 gets me negative 4h. Negative 4 times h gets me another negative 4h. Put them together, there's the negative 8h that we need. By the way, you'll also notice that this friend, it's something times itself, which means it's a special kind of polynomial called a 5, 4, 3, 2, 1. This guy is an example of a perfect square trinomial, which should hopefully tell us that I don't necessarily need to remember my perfect square trinomial pattern to be able to factor it. As long as I know how to reverse my met wet by doing some double factoring, I should be just fine. Now for number 2. At the front, it needs to be j squared. Only way I'm getting there is j times j. At the back, I need to get to negative 56 when I multiply and negative 1 when I add. Well, let me think of some options for negative 56. I know 1 needs to be positive and 1 needs to be negative if I'm getting to a negative 56, so let me preemptively slot those in there to my factors. Well, options. I could do 1 and 56. No way that's getting me anywhere near a negative 1. I could try a 2 and a 28. Again, no way that's getting me to a negative 1. I could try 4 and 14. Again, getting closer, but still not quite. Well, my last option, 56, is 7 times 8. So this option is going to do the trick. I just need to figure out which sign I need. Well, if I need a negative 1, I should take negative 8 and positive 7. Let me once again check my work by doing some metwet. I'm going to confirm that the middle term is what I want. J times negative 8 gives me negative 8j. 7 times j gives me positive 7j. Look at that. Negative 8 plus 7 does give me the negative 1j that I need. And for number 3, I see something with 4 terms, which immediately tells me that which of my special patterns is this going to be? 5, 4, 3, 2, 1. Well, when I see 4 terms, I immediately think of factoring by grouping. So my first move, I'm going to draw a big dividing line down the middle of my polynomial. I want to split it into 2 and find the GCF of each half. For 2k cubed minus 3k squared, 2 and 3 have nothing in common, but k cubed and k squared, using my strategy of taking the smallest exponent that I see, the GCF should be k squared. Let me give myself some parentheses. What do I need inside of them to get back to 2k cubed? Well, k squared, I need to multiply by 2 to get the 2. To get from k squared to k cubed, I need to add in a copy of k. Now to get from k squared to negative 3k squared, well, that's just k squared times negative 3. In the back, if my factoring by grouping strategy works, I know that 2k minus 3 needs to show up in the factors in my second group. So let me preemptively put it there. Now, I need to get from 2k to negative 2k. Well, all I need to do there is multiply by negative 1. Negative 1 times negative 3 does get me to that positive 3 that I want. This factored form works. Now, finishing off my factoring by grouping strategy, I'm going to take my 2k minus 3. I'm going to pull it out of each of my terms. That leaves me with the k squared in my first group and the negative 1 in the second. And now I'm done. Just kidding. No, I'm not. Look at k squared minus 1. K squared, that's a perfect square. 1, that's a perfect square. They're joined by subtractions. This guy is an example of some difference of squares, which means I can go further. 2k minus 3 is still part of my final answer. I can't forget about it. But k squared minus 1, if I remember my difference of squares patterns, it's going to be a binomial times a binomial. One of them's got a plus sign in the middle. One of them's got a minus. But I know that the thing at the front needs to multiply by itself to get to k squared. That's got to be k times k. The thing at the back needs to multiply by itself to get to 1. Well, that can only be 1 times 1. If you don't believe me, feel free to do some metwet, but this product of polynomials should absolutely get us back to our original in number 3. Very nice. Now, 2 wrinkles for us to unwrinkle, and then I'll set you free. With a little bit of elbow grease, we found that all of the polynomials we encountered last time were factorable. But do you think that every quadratic trinomial we find will be factorable? Maybe, maybe not. Let's try x squared plus 4x minus 3. I want you to try to factor this guy using the pattern that we discovered last time. Maybe you can, maybe you can't. Either way, we're going to see why not. Go! All right, let's do it. K squared plus 4x minus 3, or x squared, sorry, minus 4x, plus 4x minus 3. Oh my God, it's so late. My brain isn't working, but that's fine. It rarely does anyway. This is a quadratic trinomial, which means that if it's factorable, it's going to be some binomial times some binomial. At the front, I need to get x squared. So this has to be an x times an x. And at the back, the only way that I could get to negative 3, well, it could be positive 3 times negative 1, or negative 3 times positive 1. Let me try my first option. So I could try an x with a positive 3 and an x with a minus 1. The only way for me to know for sure is to check my middle term. So x times negative 1 in my check is going to give me negative x. 3 times x, that's going to give me 3x. Negative x plus 3x gives me positive 2x. This is not the middle term I want. This factored form does not work. So the only other option for me would have to be if I flip it. So instead, it could be x minus 3, flipping my sign, and x plus 1, flipping my sign. Well, again, let me check my middle term and make sure I'm happy. So x times 1 gets me positive x. Negative 3 times x gets me negative 3x. Adding those together, well, that's going to give me negative 2x. This is not the middle term I want either. So I've exhausted all of my possible options and none of them work. What do you think I'm going to call this kind of polynomial if it can't be factored? None of my options worked. I'm going to call this guy a prime polynomial. Just like numbers, it is possible to find polynomials that we cannot break down any further. This is a prime example, pun intended, of a prime polynomial. Nice! So we now know that prime is an option. It is totally possible that we cannot factor further. But most of the things that we find will be factorable. Last time, when we were working with our quadratic trinomials, we saw a way to factor them as long as they had a leading coefficient of invisible 1. Which necessarily begs our last question of our class today. Well, what if the leading coefficient is not 1? Say, for example, I've got something like 5x squared minus 11x plus 2 that I want to factor. Well, it's a quadratic trinomial, which means that if it's factorable, I should be able to break it down into the product of two binomials. I just now need to figure out what would need to go into these first two slots and into these last two slots so that I can met-wet back out to get back to where I started. Knowing what we know about the anatomy of our quadratic trinomials and the met-wet that we would want to do to confirm our answer, try some options here and see if you can figure out how this friend breaks down. Go! All right, let's give it a shot. So, when I met-wet back out, at the very front, I'm definitely going to need something that will get me back to that first term of 5x squared. And at the back, I'm definitely going to need something that when I met-wet out will get me to that constant term of 2. Now, we saw when the coefficient at the front was 1, these two numbers at the back also added to get negative 11 in this case. Let's see if that works here. So 5x squared. If I'm going to get to 5, the only way that I can do that is 5 times 1. The only way I can get to x squared is x times x, so there's actually only one possible factorization of 5x squared. It needs to be 5x and x. To get to positive 2, now I know that I can only do a 2 times a 1. That's the only way to make this work. But I know that I have a negative sign in the middle. Thinking strategically, what does that tell us here about the stuff in our factors? Well, if I'm going to do 2, it could be either positive 2 times positive 1 or negative 2 times negative 1. No way that positives can get me to a negative middle coefficient. This has to be a negative 2 and a negative 1. So both of these need a negative sign in the middle. The only question now is where do I slot the 1 and the 2? Well, the only way for me to figure out for sure is to do a little trial and error. Maybe I'll happen upon the first, or my correct answer on my first pass. Far more likely that I'll need to try something out first. So, first move, let me try putting the 2 over here and the 1 over here. Maybe it gets me there, maybe it doesn't. Well, I believe the first term, I believe the last term. Let me just check my middle term. So I'm going to do 5x times negative 1. This gets me to negative 5x. I'm going to do negative 2 times x. This gets me to negative 2x. Add them together, I get negative 7x. this is not my correct factorization. It does not get me the negative 11x that I want. So that option did not work. There's only one other option for me to consider. Let me swap the negative 1 and the negative 2. Doing some met-wet here to check my middle term. Well, 5x times negative 2, this is going to get me to negative 10x. Negative 1 times x is going to get me to negative x. Would you look at that? There's the negative 11x that I need. This is my factored form. Now, I hope that when you look at this, you will see, does negative 1 plus negative 2 equal negative 11? Well, hopefully, obviously, it does not. So this special pattern that works when we have a leading coefficient of 1, we can no longer rely on when we're working with things where the leading coefficient is something other than 1, which means trial and error is going to be our only approach. Let's try this with one more, and then I'll set you free. I've got 3y squared plus 8yz minus 3z squared. Again, I'm going to potentially do some trial and error here. I know that this guy needs to be the product of two linear binomials. What needs to happen for the things at the front? What needs to happen for the things at the back? Do some met-wet to confirm it gets you to the middle term you need. Go! Five, four, three, two, one. Let's do it. 3y squared. Well, the only way that I could get to 3y squared, it needs to be a 3 times a 1 and a y times a y. So at the front, I know it's going to need to be a 3y and a y. At the back, I have negative 3z squared. If it's negative, one of these needs to be positive, one of these needs to be negative. My only options, it could be negative 3z and positive z, or negative z and positive 3z if I flip my signs. Well, let me try one of them and see what happens. Let me try 3y and negative 3z, and then let me try y and positive z. Maybe it works, maybe it doesn't. Only way for me to know is to check. So I'm going to check my middle term. 3y times z gets me 3yz. Negative 3z times y gets me negative 3yz. This guy does not work. This can't be our factored form. So that option didn't work. Let me try another option. Maybe I'll flip it. So let me take 3y plus z, and then I'll swap that with the negative 3z. Well, over here, doing some met-wet, let's check my middle term. 3y times negative 3z is going to get me negative 9yz. Z times y, that's going to get me positive yz. Adding those together, I get negative 8yz, which is very close, but not quite, to my middle term. So there's something I like about this. The only thing that needs to change is the sign. So if I'm thinking strategically, what that should hopefully tell me is that if I flip my signs, I should get the middle term that I want. So I'm going to take that factorization from above. Because the number part I like, let me flip the sign so that I get the sign that I want. Let's check and make sure. Our middle term will be 3y times 3z, which is positive 9yz. Negative z times positive y gives us negative yz. Add them together, we do get the positive 8yz that we want. Here is our factored form.